All right, our next speaker is Mark Krieder. Mark is a PhD student at the University of Montana and the College of Forestry and Conservation. And he's going to present, I'm going to steal a little bit of your thunder right now, Mark. This is the first public glimpse of brand new research results out of the Selway Bitterroot Wilderness. Mark spent last summer leading a team sampling in the Selway, and he's got data brand new, hot off the spreadsheet.
Yesterday even. Thanks. And I'm really glad to go after Kim, especially your question was awesome. Because like I mentioned, climate can be a really big kind of turning point for forests and sort of send them off either coming back to forest or killing a lot of seedlings and making it much harder and kind of slowing things down. But you can go on to the next slide, please. But I think this figure shows how we might think of forests coming back after fire. And what we'd hope would be this green line where a forest quickly returns back to the pre-fire state. Trees come back and everything's good. We have resilience. Of course, do one more. Like Kim was talking about, climate can often sort of push us in the other direction. And so we don't have seedlings coming back after fire. We might not have good seed sources. There's no seed available. And so there's no trees to come back. And the system might kind of transition or convert into something that's kind of far away from what was before. However, these dotted lines right here kind of get at your question, being that we don't quite know what happens over longer time scales. You know, most of the research into these things and sites come from 0 to about 30, 40 years after a fire. Trees grow really slowly, not really on human time scales. And so it's unclear whether if you waited longer time spans, a century or so, would we eventually get trees back? Or is this more of a permanent conversion into shrublands, grasslands, and sort of for the next centuries, potentially, we just won't have forest here after a big high severity fire. So the Selway Bitterroot Wilderness in particular, and the Frank Church too, are really great places to answer some of these questions about how climate might impact long-term forest pathways. And part of that reason is because we have a lot of examples of really big, widespread high severity fire from about 100 years ago in the early 20th century. So we have some photos down here showing aftermath of the 1910 very large fires across Montana, Washington, Idaho. And so these places, in some places, have been growing back without burning since 1910, 1934. We have about a century of growth on these forests, and we can start to look at how climate and other things impacted the forest over these longer 100-year time scales, and sort of try to extend some of the research that we've been doing in other places that Kim was talking about across the western U.S. on these kind of more 0 to about 30-year time scales. The Selway is also very cool because we have differing post-fire climates. That was one thing that we heard about in the previous talk about how the climate after a fire in those first initial years can really, really impact if the seedlings get killed or not, or if they're able to regenerate. And here I've just highlighted 3 major fire years in the Selway Bitterroot Wilderness, 1910, 1919, and 1934. And these 3 fires were each followed by very different post-fire climates. So 1910 fires, the 5 years after there were actually pretty cool and wet, even by today's standards. Whereas 1934 fires, the 5 years after that fire, was very hot and dry, in the top 10%, even by kind of current averages under these warmer climates today. And then there's other fires like 1919 and 1900 and 1922 that fall somewhere in the middle. And so we kind of have a spectrum across post-fire climate, and can look at the effect of that on forests over decades and almost one century out. So this is what that looks like on the ground in the Selway. These are places in the colored areas where fires burned historically and have not burned since. So these are basically forests coming back after those fires that we still have available to us. They haven't been disturbed by a subsequent fire, and we can go back in and look at how that forest returned, how long it took for the forest to come back, and how the post-fire climate impacted that. Of course, we also, across the Selway, have a wide range of average climate too. And that was something that we heard about as well in the previous talk. about how it really matters if you're on a site that is just kind of normally cool and wet, or a site that maybe is southwestern facing, lower elevation, and more average hot and dry. And so across the Selway, we again have a wide range of climate, from hotter and drier, lower elevation sites along the Selway River, all the way up to cooler and wetter sites along the Bitterroot Crest and higher elevation areas. So the two combination of these different post-fire climates and different average climates make for a pretty cool natural experiment in the Selway, where you can look at fires that have occurred across these two kind of gradients. So we have fires that represent the full spectrum of these two crosses, and then we can look at the effect of each post-fire climate and average climate on how forests come back through time. And so that's kind of the third dimension to this, is that about almost 87 years of growth from the 1934 fires to 2021. So this allows us to really potentially extend some of the really awesome work that we've been doing across the Western US. And the Selway is one of the only places we could ask these sort of questions, because there's been just a lot more fire than most places, and it's been protected from other forms of logging and things. So these forests are still on the ground, and we can still go back in and look at how they've been returning over the last almost 100 years. Now, these colors right here might represent a kind of initial hypothesis for how these forests would be expected to return. So for instance, on average climate, cool, wet sites, especially in cool and wet years, maybe there's plenty of water available for seedlings after a fire, and maybe we think there's really no risk. This forest will come back very easily. Whereas in hotter and drier locations, kind of in the upper right corner, especially in hot and dry years after fire, this is where, like we were talking about in the last talk, this is where we might be more concerned about seedlings being killed after fire, and maybe there aren't any trees, at least in the initial decades. So the question then becomes, in these sort of sites, does it eventually return to forest over century timescales, or is that more of a permanent transformation into shrubs, shrub fields, things like that? So then the overall question of this research is how climate, and both average climate and post-fire climate, how that impacts the long-term forest development, and after high severity fires in particular, because these are the fires where we have much less seed resources, seed distances are much higher. So these are the types of fires that we'd be most concerned about. And we can use fires that have been happening in the Selway 100 years ago potentially as a sort of model to inform how we might expect fires that are occurring now to happen in the next century with climate change. So to do this, last summer, like Andrew said, I was out in the Selway with a great group of research assistants, and we put in 95 sites across the Selway. It might be a little bit hard to see their little circles colored by their climate groups. And these plots span about 50 kilometers square of the Selway, so it's, like we all know, a very big wilderness area, but it does cover a pretty good portion of the Selway and much of the available remaining historical legacy of these old fires. These sites were also designed to be stratified across average climate, and so we also have a good representation from all the way from hot, dry sites on average all the way to cool and wet sites. So we went in, and basically the main thing we were doing was coring trees, extracting a core so we could age the tree and figure out how long it took after the fire for that tree to come back. We cored about almost 2,000 trees for about an average of 20 per site. Go on to the next one. And so then for each of these trees, we were able to estimate the age by counting the rings and essentially, and then estimating for the time that it took for the tree to grow to the height that we cored it at. So basically trying to get the most accurate estimate of the year that tree germinated from seed and established. So with all these trees, we can then create sort of a growth curve for each site. So this shows across on the x-axis, like a year since fire, how long it took for all those trees to establish. All the way up until the very last tree that was recorded is the top. And this is an example for one site, but then we can create sort of curves from that, modeled curves, and start to look at how climate impacts kind of the shift of this curve left to right. So does it come back really soon after fire, or does it take a lot longer for the trees to return? Is that curve shifted further into the future? And then also the steepness, how quickly, once trees start coming back, do they all come at once? Or is it more kind of a slow trees coming in every few years for a long period of time? So this then is sort of the raw kind of spaghetti plot of every site in the cellway. And I only show this just to show that there's a wide range of variability. So we have sites where the high severity fire happens, and almost immediately we have trees coming back in. But then, of course, there's a lot of sites where 25, 50 years have passed since fire before we start recording the first trees. And so and I just want to also say that this is kind of recent data, and it's using about 90% of the cores, so it's not final. But there's the last cores need some extra work. They have scars, things like that, need to be resanded and rescanned. But this is a kind of representative sample, and I don't expect things to change too much. But just keep your eyes posted for the full final results. But we can start to look at what factors impact how quickly forests come back. And one of the big ones is average climate. So this is exactly what Kim was talking about in the previous talk. Drier sites, that's going towards from green to brown sites being the driest. Those sites take longer to come in after fire, and about 20 years longer. One other important thing to see here is that in virtually every single site, it takes about 15, 20 years before we started recording the first trees. And I think this is largely because these sites, we selected them on purpose to be in very high severity patches. These historic fires were massive. Like this photo showed, very large patches where almost every tree was killed. So we don't have much seed source. And so even in the wettest sites, we're seeing 15, 20 years before most of those trees are coming in. You can go on to the next slide. However, then when we were looking at the effect of post-fire climate, we actually saw something kind of opposite to what we expected and to what Kim talked about, where actually fires that were followed by drier than average years actually were the quickest to return, and fires that were followed by wetter than average years actually took longer to return. And so this is kind of opposite to what Kim talked about, opposite to what I expected to see. And so I think this is potentially for a couple of reasons. You can go on to the next. It could be just an artifact of kind of this geographic area that we were sampling in. Since the sites that were in wetter than average fire years all came from the 1910 fires, those fires occurred in one part of the cellway. And so it could just be, there's something about that fire year. Maybe we had a big masting, big seed availability after that fire, or versus another fire. So it could be these sort of these artifacts of these fires. They're somehow different from each other. For example, we could have also had potentially higher snowpack after the 1910 fires that could have killed seedlings. So it's a little bit hard to compare across years. We're trying to look more into some of these factors, into seed availability and other snowpack weather things, and to analyze if that could explain this trend. It could also be that the cellway Bitterroot, like we saw in some of those map projections, were really not as extreme or hot and dry as like in the southwestern U.S. So it could be that in this mild climate here that we have, nothing is really all that hot and dry, and so that this relationship could be a lot lessened or even reversed. For instance, if in cool and wet locations, it could be that hot and dry years actually are beneficial because it extends the growing season. It might ward off against fungal infections and other things that could kill seedlings if it's too cool and wet. And finally, it's possible that in cool and wet years, we might have more competition, more shrubs, more growth that make it harder for seedlings to return after fire. So I just showed establishment curves, but we can also look at biomass accumulation, because of course we don't care. We're interested also in as forests coming back, with a lot of biomass, both for carbon storage and also because we want forests that have a lot of trees and a lot of biomass. We like that. So this is every single tree, sort of showing how those trees gain biomass over time as they grow bigger each year. And once again, we see that biomass accumulation is longer in drier sites, which makes sense. These more productive wet and cool sites grow quicker, and this shows up in the data set that we see. After about 80 or 90 years, biomass is about 120 megagrams of biomass per hectare, but that it takes longer in these drier sites. We can also look at biomass accumulation by post-fire climate, and this is showing at every site and sort of the biomass that's accumulated in that site over time. And it becomes pretty evident that all the sites with the most biomass are all in these post-fire dry years, so fires that were followed by hotter and drier climate than average. And so kind of similar to establishment curves, kind of counterintuitively and surprisingly, these data showed that the sites that were followed by hotter and drier years than average actually accumulated biomass the quickest. And that's probably for some of the same reasons, potentially, as I talked about earlier. This could be just differences based on the geographic placement of these sites. Soils aren't necessarily the same across these sites. And so I'll be looking more into maybe some potential explanations of this. But it also shows the importance, the sooner that you can get trees on an area, the quicker biomass accumulates. And so I think this is probably being driven by the fact that those sites that were followed by hot and dry weather just had trees coming on quickest. So some take-home points to keep in mind. I think the biggest interesting point is that the forest did eventually recover. All of these sites were located 400 to over 1,000 meters from the closest intact forest edge at the time of the fire. So big patches. But after 100 years, on nearly every site, we had mature forest. So that's hopeful, even after these big high severity fires. It's important to see that just like we saw in the short term, 0 to 30 years, where drier sites had impacted regeneration, this does extend even out to kind of century time scales, and drier sites do take longer. There's this interesting kind of signal of wetter sites actually being slower, or sites that were followed by wet post-fire climate. And I think I put a question mark on there and some asterisks. It's definitely not what we would presume, and I think it'd be interesting to look into a little bit more if we can see what factors might be driving this. But I think finally, the last point I want to leave you all with is that it did take a while for these forests to come back after these big historic fires. And that is both potentially cause for concern. We want forests to come back quickly after high severity fires in the future, of course. But I think it's also a reason for maybe a little bit of hope that these forests might display kind of continued establishment over long time scales. And just because we don't see a whole lot of trees in the first 10, 20 years doesn't necessarily mean that at 100 years that might be different. So with that, I'd like to thank a lot of folks. We were really appreciative too of especially the Nez Perce and Clearwater Forests for letting us stay at the Moose Creek Ranger Station for the last 2 summers, for a large portion of the summer, to conduct this research, and for all the other many collaborators. And with that, if there's any time for questions, I'd be happy to have a little conversation. Thank you.
We've done one question.
Yeah.
Mark, did you see any areas where forests hadn't recovered? I made sure that all you told those big shrub fields running the Sully River were like product of those many fires.
Yeah, we had a few sites that were mostly, maybe had like 1 or 2 trees in them. I think we didn't have any sites without a single tree, and we deliberately put plots in kind of agnostic of whether or not there was forest on the landscape currently. And we used a product like a mapping product saying if there could be forest, if the climate and soils could support forest in theory. And so we really didn't see a whole lot of places without any trees. Definitely some sites with very few trees that maybe come in the last 15, 20 years. But I was actually surprised to not see more of those very large, complete tree-free areas.
30 seconds if somebody wants to ask me a question.
Yeah.
The tree cores you took, was that separated by species, like a lot of holes in the center, or how did it compare?
Yeah. What I showed here was for all species, and most of them were either dug for or grand fir was about 80% of the trees. But the results look very similar when you run it just for grand fir or just for Douglas fir. So I think this trend extends beyond just species, and there was the species showed up across all sites. It wasn't like certain categories only had certain species. Yeah. Thank you.